I would like to talk a little bit about simple harmonic motions, which in short is called SHM. So there are actually three conditions for a motion to be simple harmonic, and those conditions are that it should be periodic, and it should be oscillatory. And there's a third condition, which is that the acceleration should be proportional to the negative of the displacement. I'll write x for displacement, and this is the negative sign is there for showing that the acceleration is in the opposite direction as the displacement. So if I actually, this is a classical case of a simple harmonic motion. So if I pull this block in that direction, then there is a force acting on the block in this direction, so the acceleration will be towards the left. So that is represented by this here, this statement. Now so we can do one thing here. We can replace this proportionality by giving a constant of proportionality of, let's say, omega squared times x. So this is and this is omega squared because I want to make sure that this term is positive, because the whole minus omega squared x must be negative, so omega squared must be positive. And then in this case, I'll just write let's say I pull this block here, so it becomes like this, right? So if I draw the free body diagram, then I will have a force which acts like so, of magnitude kx, where k is the spring constant, where this distance is x. Okay, so Newton's second law, you know that. So kx must be equal to, this body has a mass m, times the acceleration a. So a must be k by m times x, and I'm going to put a negative sign because the displacement is in the right direction and the acceleration is in the right direction, right? Let me write it here. The acceleration is in this direction. So you can see that if we compare these two equations here, this and this, then you'll find that in this case the omega square comes out to be k by m. So we can solve further, but I want to generalize this. So let me rewrite this as a is equal to minus omega squared x, because a is much more short-handed. We know that acceleration is the double derivative of x of displacement is equal to minus omega squared x, and this is a differential equation. If you have done differential equations, great, but if you haven't, just remember that the solution of this differential equation will be of the form a sine omega t plus phi. Okay, and let me separate this out. That's okay. So this is the solution of this differential equation. You can check it for yourself. If you differentiate x, which is this here, if you differentiate it twice, then you'll get minus a omega squared times the sine of blah 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 something inside, and that should be equal to minus omega squared times x, which is a times this stuff, a times sine of whatever. So this sine of whatever comes cuts out, it cancels with this, a cancels with this, so you get minus omega squared is equal to minus omega squared. So you can see that it satisfies our conditions. Okay, so this is the general equation, so let me write it here. X is equal to a sine omega t plus phi. And if you are familiar with trigonometry, then this can also be written as a times cosine of omega t plus phi minus pi by 2. Oh, actually I wrote it opposite. It should be pi by 2 minus omega t plus phi. And now if you simplify this further, you will get this as a times cosine of pi by 2, actually not pi by 2 but omega t minus omega t plus some other constant, let's say omega is already used, so let me write, there's one more phi like that. Okay, you'll get something like that where phi is this phi plus pi by minus pi by 2. Yeah, so you must also know that cosine of minus theta is cosine of theta, so this becomes a times the cosine of omega t minus phi, and minus phi is another constant for which I'll write plus phi. So you can see that there are two forms of the same thing. So the two forms, this is more easier to deal with. So let's take this as our general formula for the displacement of a body in simple harmonic motion as a function of time. Now you can play with this and you can differentiate it again to get that v is equal to a omega cos omega t plus phi, and you can differentiate that again to get that a is minus a omega squared sine of omega t plus phi. So these are some basic things you need to remember, because this belongs to the heart of SHM. Most of the problems deal with this. And there's one more thing that I forgot to mention, is that the omega which we have defined here, this omega is called the angular frequency. The angular frequency. And there's one more parameter except displacement, velocity and acceleration, is the time period of the oscillation. And in the beginning I said that it is periodic. There it is, it is periodic, which implies that there is a specific time period for its motion, and that time period is defined as 2 pi over omega. And this omega should not be confused with angular velocity. It is very confusing because we have the same symbol for two completely different things, but in certain cases they actually become the same. Angular frequency becomes angular velocity because in cases like uniform circular motion and etc. But in this case it's just omega, and I'll write this as angular velocity. Oh, sorry. See, I got confused too. This is angular frequency. Okay, so this is the time period of oscillation. You can prove it to yourself by using graphs or something. I won't prove it in this video. And so these are some things you need to remember, and we'll use this in our future videos. So yeah, that's it. I hope you like it, and I'll see you in the next video.